I'm going to do another proof looking at this simple pendulum. Like all proofs, you don't need to memorize it. Hopefully you can follow along, and when you see it, you can kind of get where things are coming from and where things are going, and then we'll just use the outcome at the very end. So we're going to consider a simple pendulum. That dotted line is our reference line. That's our equilibrium. A vertical line, that's where a pendulum tends to fall to when there's no energy. That's where the net force on it in terms of the vibration drops to 0. Now let's say we've got a string with a length L. So that side's L, that would be L. We put a mass on the end. Oops, let's draw that differently. Let's say we put a mass on the end. It's at some arbitrary position theta, but more importantly, it swings through kind of following the pizza crust of a chunk of circle. It's at some arbitrary position S. So this pizza crust distance is S. If I can show that the force acting on the pendulum is proportional to S, really what that means is if I can do a free body diagram and some component work and show that F equals some constants multiplied by S, then I've shown that it's simple harmonic motion, and whatever I get as those constants, I can sub into those equations from the last proof. There's two forces acting on our pendulum, gravity acting straight down, and the tension pulling towards the center of the circle. When we learned about forces and things on funny angles, the method to solve it was to consider the direction it's accelerating in. That's the important component, is how I worded it way back when. In this case, a pendulum, the motion's kind of complicated. Tension's pulling it towards the center of a circle, going through centripetal motion, and gravity's making it change velocity as it gets faster and faster towards equilibrium, and then slows down as it gets to the other amplitude position. So tension's making it accelerate centripetally, and gravity is making it accelerate along that pizza crust. It's the gravity that's the important force. At this split second, the important component is tangent to the circle. That sort of linear acceleration along the pizza crust is what we're looking at now as we look at the vibration. It's almost like we took a mass on the end of a horizontal spring, but instead of having it track perfectly left to right, it's sort of following a circle back and forth. So free body diagram, that tangent force, that's the one I want to find. That's the force that's whipping it back towards equilibrium and then making it slow down and bring it back to the equilibrium. That's the restoring force. If I can show that tangential force, that component of gravity, is proportional to S, then we've got it. To find that force, we're going to turn this into a triangle. This would be the perpendicular part that I don't really care about, but I want to find that restoring force, the one that I labeled as F. I've drawn a triangle, so that means I've got to connect that angle theta somehow into that triangle. This gets a little bit ugly, but I think we can figure it out. If I were to track gravity backwards, the same angle theta fits over here. If I were to extend this tangent backwards, now we can do a little bit of work. So it's kind of messy. I've got a Z pattern. There's a theta that fits in here. That means that opposite angle theory, this side is also a theta. That means that this angle between F and FG is 90 minus theta, which means that this angle way down here inside my triangle is the same angle theta. So it took a little step and a little bit of work, and it's a little bit messy. Let me see if I can clean that last little bit up. Theta is this angle at the bottom of the triangle. That means that my restoring force, it's opposite that angle. It's gravity multiplied by the sine of the angle. We know that gravity is mg, so we know that gravity is mg sine theta. This is a disaster. This is not F proportional to S. If anything, I've gone the wrong way. I've disproven our point. I was hoping to show that F was proportional to S. I've shown that F is proportional to the sine of theta. So far, the simple pendulum is not simple harmonic motion. To get out of this, we're going to have to do an approximation. So math trickery. A pendulum is not simple harmonic motion unless we consider a special case. If we look at a pendulum swinging through small angles, then I can go a little bit farther. there's a small angle approximation that says sine theta, if the angle is small, is basically the same as theta. If I asked you to draw the sine curve after, I think it's grade 11 math, you would all draw me this nice little swooping sinusoidal thing. But if we zoomed in and just looked at really close to the origin when theta was small, if we just looked at that part of the graph, it looks like a straight line with a slope of 1. Basically looks like y equals x, or in this case, sine theta equals theta. So by using this approximation, by using this special case, if we only consider a pendulum that's swinging with small angles, then we can say that our restoring force, instead of being mg sine theta, is mg theta. Still not simple harmonic motion. But we can get out of this. If I go back to my original diagram, I'm going to draw it a little bit differently. Our equilibrium position, that's the length of the string. Some arbitrary position over here, that's also the length of the string. It's out some distance s. The angle theta fits in up here. I know no one likes doing it, but if we consider radians, the definition of an angle when we're in radians is the arc length to the radius. So using these letters, theta is the arc length to the radius, s over L. If I substitute that in, my restoring force is mg s over L. Or if I rewrite it, the restoring force is mg over L multiplied by s. This, finally, is simple harmonic motion. We've shown that the force is equal to k times s. Just instead of a boring old letter k is this expression, mg over L. So all those crazy equations we came up with before, we can apply to a simple pendulum, as long as the pendulum's got a small angle. Wherever we see letter k, just sub in mg over L. Here, I'll do one quick one. The time period equation. Time period is 2 pi root m over k. If I'm curious about the time period of a pendulum, wherever I see k, sub in mg over L. So I get t equals 2 pi big square root m over mg over L. We've got a fraction on the denominator of a fraction. Nobody ever likes that. Take a minute, do like an invert and multiply if that helps. But what happens in this case is the m's cancel. The L on the denominator of a denominator flips to the numerator, and we get that the time period of a pendulum is 2 pi root L over g. I'm not going to give you that equation. When the equations are up on the wall of the classroom, you won't find that, but you will find t equals 2 pi root m over k, and for a pendulum, k equals mg over L. And I expect you to be able to do the